Welcome to the ASTRO. So in this Python tutorial, we are going to learn that how to fit any periodic function such as a sine omega t, where a is the amplitude of the sine and omega is your angular frequency. Okay, so let's do it. Okay, so for example, you can see here I have here example of periodic iterative plot of temperature versus date, and you can see that the temperature seems to be greater maximum and minimum, so it's periodically falling and rising. So like how to obtain a profile for this uh, temperature and date, and you can ask, and you can like also predict like what will be at any later time using this profile fitting. So let's do it. Okay, so first I will import some libraries. So import library. So I will import numpy. So import numpy as np. So this will like deals with your number, deals with array, and then I will okay, so then I will like define our x and y data. So I can define our x equal to np dot linear space. I want to go from -10 to 10, and I want 50 data points, right? And y equal to, I can say 50 into np dot sin x, right? So this is like a simple xy data. So x is here and y is here, right? Now we want to simply plot it. Okay, so here you can import matplotlib dot pyplot as plt. So this is deals with plotting, and I will also import random module. So import random. So this is deals with random numbers. Okay, now you got your x and y data, right? So what I'll do, I will add here some noise. So y equal to, I will add here y equal to data plus noise, right? So for adding noise, I will do here, I will put here np dot random dot rand int, and I will add some number from 1 to 10, and I will give equal number to the x size of an array. Now there should be random, this should be in, right? So this is like act as a noise. So this part is a noise, right? So this part is a noise, right? Now I will simply plot it. So plt dot scatter x comma y. So here you can see that you can make some numbers, say 100, and here 100 also. Okay, so here you can see that this plot also looks up periodic plot. Okay, it is varying from minimum to maximum and then coming back. Okay, so what we will do, we have to open a profile uh, for this uh, line fit, that what how its profile look likes uh, for this scatter plot. You can also increase the noise in that plot. Okay, so here it goes. Now suppose I want to fit it, okay, using a sine profile, right? So uh, now we have to fit data points with sine profile A into sine omega t. Okay, so for t we have x. You can make it here t equal to something, then t, right? So t should be here, t and y. Now it's fine. Okay, so we have to fit this profile using a sine curve. Okay, so for that I will import from scipy dot optimize. I will import curve fit, right? So this will use to fit curve, right? Now what I will do, I will define here a function. So we define here, define profile you want to fit. So I will define here, define sine, and then I will put here our t variable, then our amplitude a, right? And then okay, so and then you want to put your omega, right? Want to put your omega. So you want to put your omega. So close it, and you can define a profile as a return. So return a into np dot sine omega into t. Okay, so this will be our profile to fit. So this becomes our profile. Now what I will do, I will type here p of 50 is your optimized parameter and p covariance is your covariance matrix. Okay, so and I will type here curve fit, and I will pass my sine function, my x axis data and y axis data, right? And I will also give some initial guess to the this fit. So I can give it say 45, and I can make it 1, right? So here I can write about things. So POPT is your optimize parameters, and which is equal to your a and omega, and p covariance is your 2 cross 2 matrix, and this will like find error in a and w, right? And p0 equal to your initial guess, right? So these are the some keywords for the curve fit functions. Now now run it, and so we have fitted the our sine curve. So you can see here, this is your pure PT, and P covariance is your this matrix. You can see this is your matrix, right? So what I'll do, I will like plot a curve. So plot fitted curve, right? So for that, type here plt dot plot your t data, and then uh, your sine curve, and pass your t and a star pure pt. So it will take your parameter together, right? Now run it. So here you can see that your curve has been plotted. Maybe you can give some value as a 50, or maybe you can give, yeah, it's fine, no problem. Okay, so we have fitted the sine function. Now so you can print here, print a, and maybe you can do it later, so keep it here. Now we have this much we have done, so you can give label to these plots. So give here label equal to data, and you can give here label equal to a profile fit, or just say best fit, right? And type here plt dot legend. So maybe you can give a different color to this plot. You can say black color. So here you can see that your curve is fitting for these data points, right? Now what else you can do? uh, you can obtain its automatic parameter. So this is your, so you can print here, print a and w parameters are POPT. So you got here, and then you want to like find error. Okay, so here is your fitted parameters, and here you can find how much error it is. So find error in a and w. So for that you have to do two things. Okay, so take here np dot, or just call it error equal to np dot square root. Okay, and then take diagonal of your p covariance matrix. So if you put here error, then this number comes. So this is like your error in your fitting parameters. So you can print here, print error in a and w is error. So So this will I give your error in your fitting parameters a and w. Okay, so here you can notice that your peak of your sine function is not fitting in this plot. Okay, so for fitting that, what I can do, I can add one more additional parameter. Suppose I add a parameter called c, and then here also c, and then add some inside gets to this parameter as a 10. Okay, and then run it. So here you can see that the curve is almost fitted. Okay, and then you can check the parameters. So this time it's 43 around 1 and it's 9.71. Okay, and then you can also check the errors w and c is, and here and c parameters are okay. So here you can check that this time the plot has got a better fit compared to our earlier plot. Okay, so this way you can fit your uh, this way you can fit your plot in better way by adding a to constant parameter to this plot. Okay, so